Hello, good day, everyone. I'm Damian Robinson from Avia-GIS. Today, we're going to have our first webinar for this year. After 3 successful webinars that was done last year, we have Guy Hendrickx from Avia-GIS, and he will focus today on sample sizes. Basically, the question is how many samples are needed for a robust spatial model. Not much has been discussed or written on this topic, hence the opportunity we have today to delve deeper in this material.
Okay, hi Damien, thanks. Am I online?
Yes.
Okay, thanks for introducing me. Damien is working with us with Avia since a while now. And with the R&D team, we've been working over a certain period already on this issue of sample sizes. So it all starts from the perspective, what's the problem? We do have, I mean, this is maybe a slide that and maps that people have seen a lot of times, but they still are extremely relevant, is that we do have an issue with emerging infectious diseases, of which vector-borne pathogens or vector-borne diseases are a very important part. These are upcoming due to a certain series of drivers. Some of these drivers are global. We think and that increased traffic of people in group is actually absolutely the main driver. I mean, bugs, vectors, and pathogens are traveling either through goods or through people. And then on top of that, of course, climate change has this enormous impact too. And then, of course, you have a set of local drivers. These are mainly focused on societal changes, which also induce land use, land cover changes and environmental awareness. Now, given that we have these all emerging issues, the need for precise information on distribution, abundance, and spread of the vectors involved with vector-borne diseases and the diseases they transmit increases a lot. So we need a lot more information on how they are distributed and how much and how they can be quantified. So field surveys are labor-intensive and expensive. The workload often is the key factor in this kind of activities. But on the other hand, these costs can be reduced by combining strategic sampling, which is sampling as little as possible, but at the right places and at the right moments, and actually combining that with spatial models using remote sensing, and of course, any other environmental data which are available. But, and there you got a second, but this requires various types of expertise. You need statistics, you need spatial modeling, you need field experience, etc., and access to state-of-the-art tools and remote sensing data. Well, this is exactly why we developed VECMAP, is to give the opportunity to people who are not specialists in all these things, who are, for instance, entomologists or field workers, and they don't have all this statistical baggage. They are not fluent with R. It's said, yeah, but you've got all these solutions in R. Yes, you do have them, and please use them if you can. But many don't have the training or the background to do that. So that is why we develop this kind of software. But anyway, what needs to be mapped? That's the first question. And it's quite interesting to have a closer look at this. Often it's shown as a triangle. There's the vectors, the host, and the pathogens as a triangle. We prefer to look at this in this way. You know, the vector is living in a global climate. Within that climate, you have an environment where part of the environment is going to be suitable. In that environment, you have a habitat, which part of it is going to be occupied. There's no single known species, being it a vector, a pathogen, or a host, which occupies 100% of its potential habitat. The same is valid for the host. The host is living in a general climatic conditions. Within that climate conditions, it has a preferred environment, a preferred habitat, and it occupies part of that preferred habitat. So if you talk about vector-borne diseases, it all happens where these things meet together. And for the vectors and the hosts, it's quite clear that this that climate, environment, weather can have a lot of predictive power into identifying where these two may meet. But if you add the disease, and that's the nice thing about vector-borne diseases, is that these pathogens are extremely protected, and they only occur where the vector and the host can meet. That's where they can spread, because by definition, a vector-borne disease will not be able to spread outside the vector or the host. You do have some exceptions, of course, like all the time, like in any classification. But it is quite clear from here also that environmental variables are going to be pretty good to map vectors, eventually also to map hosts. It's already going to be a bit more complicated to map where hosts and vectors meet. And it's going to be even further complex to map pathogens, vector-borne pathogens, because they also will depend about non-environmental factors, and these non-environmental factors are going to become more and more important. For instance, management of diseases or the management of hosts will have an impact, whilst vectors are free-ranging species. Anyway, it's important to know you can use environmental variables to map vectors, hosts, and pathogens, but not always as accurately. So how can satellite imagery contribute? If you talk about smart sampling, you want to sample as little as possible and then extrapolate that using, in our case, mathematical formula, a statistical or a mathematical, and then extrapolate. So the art of the game is to select the right spots to measure. For instance, if this is a map of a country and you want to estimate in each grid cell what is the probability of presence of a given vector, you want to sample as little as possible to reduce the costs. And then you would combine that with covariates, a set of covariates which are available for the entire set of grid cells. And then you can calculate, given that formula, that's what spatial modeling is, the probability of presence, knowing the environmental settings within the areas where the vector was found and where the vector was not found, and then you can calculate that probability. So this is what happens. For the story, not everybody is aware of that. For doing this, we use polar satellites. These are satellites which are orbiting from north to south pole. And in the meantime, the Earth is turning around. So actually, these satellites are having just one route, but it's the Earth that is moving. And that's the nice thing of engineering this stuff, is that in 24 hours, often they plan a full coverage of Earth. And if there's twin satellites, it's even possible to have a full coverage in 24 hours of daytime and nighttime. Anyway, that's just another part of the story. So now the question is, we want to sample as little as possible to get the best results. So what is that ideal sample size? So we've been working on this from an empirical standpoint. And the first step was to create a virtual vector, because one of the problems in catching, in relying on real data is that you can catch a vector, but you're pretty sure when the catch is positive, but you're never sure when the catch is negative. So to avoid that problem, to avoid false negatives, being negatives which are not true, we generated a virtual vector. Then we identified some test areas, computed spatial models, and went to estimating the ideal sample size. So to create that virtual vector, we used an existing algorithm. It's an R. We can share with you the details if you want to. It is called SDM V species, and it's a very efficient algorithm. You select a series of climatic variables, and you can then compute it. We were not using hard classifiers, but rather functions to allow for a more realistic output, and that's the output. So this is our virtual model. This is just a non-existing vector, which is actually living in a certain habitat, which is part of an environmental environment and a general climate in Europe, and which now gives us a 100% distribution pattern we can start working with. Of course, for the purpose of this work, you can also hard classify it, present, absent, instead of having more classes. And then we identified a series of test zones. We selected 10 zones which have different patterns. Some have overly dominant present, some are overly with a dominant absence. And we all took as a size of these zones 400 by 400 kilometers. This is rather empirical. We could choose any size. And as an example of different suitability, like for instance, zone 3 is about 50-50. Zone 4 has a more presence, and zone 8, for instance, has more absence. These are the 3 which we've been focusing on a bit afterwards. Once we had this, we started computing spatial models. So we were running a series of models to be able to extract statistics. We used random forests algorithm, and we used 10 sample size categories. For instance, is it possible to map presence absence with 10 samples, 25, 50, 75, 100, 250, 500,000, 2,500, and 5,000. We repeated that in each of the 10 zones and tested also separately balanced or unbalanced sample sets. This is quite important because often in scientific publications of spatial modeling, the sample size, the sample sets which are used are not balanced, and we wanted to test if this has an impact on the quality of your model. So we tested 50-50 ratio and very unbalanced 10-90 ratio. And then, of course, the model outputs were compared with virtual vector to compute statistics, accuracy statistics, the same way everybody does when doing a spatial modeling. So the statistics we computed was Cohen's kappa. This is a fairly classic one, area under the curve, the percent correctly predicted or classified, sensitivity and specificity. And then once we had these graphs, you will see them in the next slides. We did a threefold assessment of the results. I mean, are the statistics, what kind of threshold is sufficiently high for each statistic? This is known from literature. Then how do our box plots behave within these graphs, and would additional samples generate? From which stage on do we have marginal benefits? This is the first output. So we here take the kappa, Cohen's kappa index. The rule of thumb says that when the kappa is above 61 up to an 80, we start having substantial models quality. So if you look at that range, the yellow bar shows you the range kappa 0.6 to 0.8. You start having reasonable outputs from 100 to 250 field samples in a 400 by 400 kilometer grid at various prevalences. And so which is that first outcome. The second one, when you look at the area under the curve, for this one, for kappa, it's quite interesting to show that the balanced data set, which is in blue, is performing a lot better than an unbalanced data set, and quite spectacularly different. So of course we were using extreme values, but all the rest should be somewhere in between. Whilst with area under the curve, these differences kind of disappear, which again shows you that you never should base your decision on a single statistic, but you always should use a set of statistics to kind of come to a conclusion. So here, the rule of thumb for area under the curve is that you should go above 0.8. From 0.8 to 0.9, it is considered to be an excellent output. And here again, you start having very good results between 100 and 250 sample size with the given test setting, of course. And what is really interesting too is that the statistics of the area on the curve, the box plots are very narrow, which means that you don't have a lot of variability. which is good, especially because we were testing a wide range of habitat suitability prevalences, we could call it, and that you end up here. You got you come close to 1 even, but then with 5,000 samples. But you have very good results with 100, 250 samples. We could actually say for the area under curve, 75 to 100 may be enough. Anyway, then we have the percent correctly classified. And here again, you look at the box plot, narrow, consistently narrow, within the range. And again, you start having stable models from between 100 and 250 samples. But here also, you do have a difference, significant difference between the balanced dataset and the unbalanced dataset. When you look at sensitivity, and sensitivity is, I mean, I always have a problem remembering what sensitivity means. It is predicting correctly the positives. And here again, you have, of course, a big difference between balanced and unbalanced. And you again have very good results starting at 100 to 250 samples. The final statistic we looked at was, was the specificity, or is the specificity, and here it is correctly predict negatives. Now, here, not surprisingly, the unbalanced dataset is performing very well. Well, remember, the unbalanced dataset includes 90% negatives, so you actually are overfitting your model. This is a real nice example that this kind of, you may say, I mean, this statistic is wonderful. No, it is not. It is just overfitting. It is not, I mean, it's not useful. Whilst when you look at the balanced data set, the negatives, the specificity is the one performing least from 100 to 250 data samples points. So now we have what can we conclude from this series of statistical analysis is that balanced data sets produce better results than unbalanced data set. I think that's quite clear. So this is a plea for when you do spatial modeling, please don't over include one class. If you have too many of one class, just reduce that class. And there are ways to do that. We can discuss if you want to. Results are fairly consistent independently of the statistic used, which is interesting. Each of the statistics goes into the same direction. And of course, it can be documented, it can be discussed. And that's always an interesting part of the discussion of your work when you do a spatial modeling paper. And you mean the different results obtained with different statistics can be discussed. And the optimal sample size lays somewhere between 100 and 250, which is good news because that's not that much. Especially in an area of 400 by 400 kilometers, which is a lot of square kilometers, you still have that this rather small sample size can give very stable model outputs. And an interesting part is also when you go more than 250 samples, you only have marginal gains. You've seen that there is a leveling out of that curve. The box plot is not improving. And you don't gain a lot in your statistics value. So now we have a sample size, but there still is a big but. I mean, how do you translate that in field? Because don't forget, we have done this knowing what was positive and what was negative. Whilst here in the real world, you don't know. So if you go to a field and you go for and you have money for 100 samples, you never know how many positives or negatives you're going to find. So we need now to estimate how many field sites need to be visited to obtain 50 to 125 positive samples. Remember, we always focus on the positives in this kind of work because we are absolutely sure about the positives. So to generate, now we need to do some additional work to actually estimate that. So this is a simple calculation. This is a very simple calculation. You have on one side, on top, the expected suitability. Remember, we had test sites which were like 28% or 60% or 48% suitable. And you multiply, and you have the number of sites you want to, the number of positives you want to obtain. It's quite clear that when you have 50-50 a chance to be positive, and you want to collect 50 positive samples, I mean, you will need to go for 100. You need to go for 100 field visits. That's quite clear. You just one chance in 2 to get a positive. So in general, 100 field visit will yield 50 positive samples. But if your prevalence or the suitability is declining, you will need to go for more samples. And that's the thing, is that you never have a 50-50. So if there are less positives than 50%, you will need to increase that sample size. So the limit set may be higher than what we calculated previously. Now we've been testing that, and in addition to this is just the statistics. So now we need also to calculate the confidence limits. So we know that if your prevalence is declining, the prevalence of suitability, the proportion, let's say the proportion of suitable grid cells is lower than 50%. The proportion of positive grid cells is lower than 50%. You will need more than this original 100 samples. But then also we can calculate the confidence limits of this. We use for that 3 of the sample sites. This one includes 48% suitability, this one includes 60% suitability, and this one includes 28% suitability. So we use that as benchmarks to estimate the confidence intervals or the confidence limits. And so when you are in a 48% suitability and we want to obtain 50 positives, we need 104 samples. 48% is a bit less than 50%, so we need more than 100 samples, plus minus 6.3, which is still very okay. So you would need to go to the field 104 times, and plus 6 would be 110 times. For 125 positives, we would need 250 samples, plus minus 10. In a situation where you have about the same number of positives and negatives. When you have more positives than negatives, these figures are a bit lower. And again, there is this is the margin we need to include. So you would need to go for 91 samples, or 200, a bit more than 20. And in an area where you have a lot less suitability, and that is maybe also often the case, you will need, of course, more than these 100 samples. You will need 161 samples in the case of 28, theoretical, plus minus 11, which is still reasonable. But if you go for 125 positives, you will need 429 samples, which already is quite a lot more. And so part of the trick to identify the proper sample size, or the needed numbers, field visits needed to get enough data for a stable model, will be in assessing what is going to be the prevalence. And of course, if you don't know it, you'll have to rely on some expert advice to do that. And this is a classic problem in epidemiology. It is, if you want to predict or do a sampling in an area where a disease is very lowly prevalent, you need very large samples. And if you want to sample a disease in an area where it is very prevalent, where many animals have it, you will need less samples. It is the standard. So this is, in practice, some examples we had. Actually, interestingly, this was a project we had in Belgium to map mosquito diversity. This is and we had 1,000 samples. And then we built models. We did the opposite. This was also about to test how many samples are valid. And you see that the model for 200 samples is giving very reliable, very comparable results as a model with 1,000 samples. So at a lot less cost, we could produce quite stable models. In Kenya, we did a similar exercise. This was with the tick, Rhipisyphilis encephalitis. This was a typical example of a desk study where there were historical records, but that allowed us to play a lot with this. They had more than 2,000 records. So the model with 2,000 records, the full model gives you this output. but you can see that even for an area in Kenya is 500,000, is more than 500,000 square kilometers. And even there, somewhere between those two, you start having really interesting model outputs in between 100 and 500 samples for such a large area. Of course, Kenya is quite discriminated. These are lowlands and these are highlands, but anyway. So finally, I mean, we would like to invite everybody for a VECMAP free trial. We can provide you VECMAP freely with a data set actually to do the kind of work I've been showing here. We've been focusing on zone 3, where it's about 50-50, but we provide you with whatever information is needed to run these kind of models and to learn to use VECMAP in spatial modeling, and together with the manual, of course, but also some online support as you need it. So you're very welcome to contact us after this webinar or in the coming weeks. So thank you very much for your being present at the webinar, and open for questions. Thank you, Damien.
Okay, thank you, Guy. Thank you very much for your insightful presentation. Please feel free to post your question in the Q&A chat box. I already have my own question. Oh, we have a question I'll get from Oliver. Thank you. He asked, why was your unbalanced sample 10% positive, whereas in real life, often you have positives in databases and few negative samples? Does it matter for the results?
That's an interesting question indeed. And here you come to, actually this is a topic we will address in one of the following webinars, is generating pseudo absences, because indeed in many databases you don't have a record of absences. So I mean, field workers often don't, they bring samples to the lab, and then the lab identifies the mosquitoes or the ticks, and the records only contain we've been sampling there, and that's the ticks we found or the mosquitoes we found. So it's a good point you make. But we wanted to actually test here if you have all these negative samples. I mean, if you have an unbalanced data set, how is your model behaving? And of course, it's somewhere in between this extreme example we use and actually the 50-50 example we compared it to. Now, there are systems that actually model without absence data. We're not in favor of these systems, especially also because this is somehow a fake simulation, because these systems compute themselves absence data without the modeler being in control. So what we do is we have a system to generate pseudo absence if you miss them. But we will discuss that in more detail in one of the upcoming webinars. Over.
Excellent response. And yeah, pseudo absences is already a feature. Well, the generation of pseudo absences is already a feature in VECMAP.
Indeed.
Yes. Have you read his response?
No, I have
okay.
no view of whatever is on the chat.
Yeah. He says, well, thanks. Another question. In your theoretical exercise, you informed your samplings by the expected prevalence. Is there a risk of circularity of targeted sampling? And what is the effect of that? Did you investigate that?
I will honestly confess that I don't understand the question. The circularity in?
The risk of circularity of targeted sampling.
I will call for a helpline here. Cedric is listening too. He may have understood the question, and he will provide some additional comments.
Can you hear me?
Yes.
Yes, we can hear you. Thanks, Cedric.
So we didn't really factor that in yet, but you're afraid of the self-fulfilling prophecy, right? So I understand that you could. We didn't factor it in, but it was a concern, and that's why we also did so many replicas to try to mitigate it at this stage. That is one of the things we will look at in the future work.
Okay.
So hopefully that's enough a response.
Yeah, no, because Olivier responded to me just because. But that's why we use the virtual vector, Olivier, so we know the full distribution. That's why we didn't do this with real data set, where you always have the risk that you don't cover your full extent of the disease, of the vector, sorry.
Okay. An interesting question.
Okay, is that there is an issue with sound here? Can you hear me?
Yes, we can hear you.
So yes, that's I heard the answer.
Okay.
That's indeed the point of using the virtual vector. Is we want to be absolutely sure and to eliminate that unknown factor.
Rafik asks, he thanks for the presentation, and he has a question about rare species where the number of positive observations is low, under 50. How would you deal with this?
Question, I mean, if the number of positive observations after going to the field is too low, you have to go back to the field. There is no work around it. Negatives, you can always eventually. Negative, you can always eventually. How would I say, deal with? But positives, you definitely have to go back to the field if you don't have enough positives. Yes.
Okay. Thanks for the response. But I have my own question. So, Guy, what is the next step?
Okay, good. Yes, well, actually, we've already talked about that a bit in the ongoing questions. We are currently working on first repeating more models. We now know the window in which we should look for more precise data. So this is somewhere between 50 and 300 field visits or samples. And there we're going to run larger numbers of models to get stronger statistics, so that we can include a tool in VECMAP that actually will help people when taking their decisions. Also taking into consideration the variability of the environment. I mean, it's quite clear that if there is a lot of variability, the issue is slightly different than if the environment is very uniform. And also other factors, but we also look at in the coming webinars we will talk about pseudo absences. That definitely is an interesting topic. How to deal with that? How to compute them and how to integrate them in these models, and also another one about and that's another aspect of spatial modeling, is often data are collected in a given area, like for instance zone 3 of our virtual vector. If you have only data of zone 3 of the virtual vector, where could it be extrapolated in the rest of the area? It is definitely can be used to model the entire area, but part of that area can be modeled, and so we'll have a webinar dedicated specifically to that too. Over.
Okay, thank you. Any more questions, or would you like to take a next question?
Are there still questions in the chat? I have no view of the chat on my screen.
Okay. can you say something about the relative weight of certainty about positives versus negatives? Because you can never be 100% sure if that is truly absent. Are they weighted equally in your exercise?
So that's why we used the virtual vector, because if we have an absence in the virtual vector, we know for sure it's absent. When you work with real field data, that's will be covered in the webinar of the pseudo absences. Because in the real field data, you never know for 100% sure if an absence is an absence. Again, that's why we did this exercise with the virtual vector. But the field data will be covered in another webinar.
Okay. Well, thank you.
Yes, this is indeed important. When you do this kind of trials, you need to eliminate as much as possible these kind of issues and then introduce them one by one. So this is what we're doing.
Okay. Someone asked if VECMAP is available online or is it a PC program? So to answer that question, it's a program that you can download to your computer. We support Windows, but you could also run it via on a Mac using a Windows platform. To download VECMAP, firstly you have to fill in the form via vecmap.com, and that's where you can submit your free trial request, and then we will follow up individually to each request, and so we can begin the free trial for 1 month together with the data for zone 3 and the variables with the download. So please, we invite everyone to submit a request and we will follow up with them so you can begin experimenting with the data sets together with VECMAP.
Okay, thank you, Damien. Indeed, that's it. So
yes, the link has been put in the chat. So to try VECMAP, and VECMAP is not only about modeling, but you can also use the opportunity to develop a field work strategy by developing custom forms as well. So you could also try that out. Okay. Any other remarks, Guy?
No, I'm fine. I'm great. Thanks a lot for everybody to participate. You can close the webinar if you want to.
Okay. Well, thank you very much to everyone viewing. This webinar will be available on our YouTube channel, so we will post that up as soon as possible. Thank you and enjoy the rest of your day.
Thank you very much. Bye-bye.